Hi everyone. In this video, I'll be discussing how I improved the performance of my regressor for the RECS dataset and how I assess and improve its fit to ensure strong generalization performance. My primary objective was to minimize the MAE or mean absolute error on the Kaggle test set while ensuring that the model was neither underfitted nor overfitted. I started out first with my baseline model being a simple linear regression model, and this gives me a reference MAE and allowed me to evaluate whether more complex models were actually adding predictive power. And in this learning curve, we see that the training MAE and the validation MAEs tends to collide to each other, and the gap between each of them stabilizes as the training set of data increases, proving that linear regression is a good model for this data set. However, the baseline showed relatively high validation error, up to 10.374, suggesting that the presence of potential nonlinear relationships in the data that perhaps the linear model simply could not capture. So then I implemented the next model, which was a simple decision tree regressor. I did a decision tree regressor, and the decision tree si did not significantly reduce the training error um, compared to the linear regression. The MAE after tenfold of cross-validation was 13.772, and the learning curve between the training MAE and the validation MAE is very, very far off, signaling that decision tree is not a good predictor or regressor for our model. Moving on, I tried random forest regressor. And so the random forest reduced the gap of the high variance and overfitting of decision tree, averaging across these trees and lowering the variance and therefore improving the generalization. And while the tenfold MAE proves to be better than the linear regression and the decision tree of 9.784, the gap between the training MAE and the validation MAE was still quite large, potentially telling us that the random forest regressor is still not an adequate regressor for our data set. Next, I then move on to gradient boosting regressors. And as we can see, the tenfold MAE from gradient boosting model was only 9.391, much, much more lower than our other model. In addition, the training MAE and the validation MAE um, seems to be coinciding together, and they're stabilizing as the training set of data increase. This proves that gradient boosting is probably the best base model for our data set. Um, So for in terms of tuning the gradient boosting data set, I systematically tuned the number of estimators, the learning rate, the maximum tree depth, the subsample ratio, the max features, as well as the loss function, including Huber loss. Instead of aggressively increasing complexity, I use a lower learning rate combined with more estimators to create smoother function approximation and better bias variance balance. Using subsample one less than one introduces stochasticity, which reduces variance. Switching to Huber laws improve robustness to outliers in energy consumption, which is important because energy usage often contains extreme values. Each iteration was evaluated using cross-validated MAE of tenfold. To ensure the reliable evaluation, I use k-fold cross-validations of tenfold across all of my base model. This was important because it reduces the dependency of a single train or validation split. It gives a more stable estimate of generalization error, and it reduces the variance in performance measurement. I use MAE scoring and converted it properly for interpretation. This ensured my model selection decisions were data-driven, incorporating the MAE from tenfold cross-validation, as well as the results from the learning curve. I also experimented with XG boosting and ensembling. Um, for XG boosting and simple ensemble averaging. And while these models performed competitively, the tuned gradient boosting model with subsampling and Hooper laws gave me the most stable validation performance, both on my MAE, reducing it to 9.134, and in the Kaggle MAE as well. The final GBM model has a very, very low MAE compared to other models, and the learning curve um, depicts that this model learns our data the best so far out of all the current model. In terms of improving performance, the model is also well fitted. I implemented a custom learning curve function that plotted the training MAE, the validation MAE, across increasing training set size, and this allowed me to visually inspect model behavior. If I see that the training error and validation error were both high and close together, that would indicate underfitting. If training error was very low, but validation error was much higher, that would indicate overfitting. And in the best gradient boosting model, the learning curve showed that training MAE is slightly lower than validation MAE. There is a small and stable gap between the two, but they are converging as the training size increase. This proved that gradient boosting is the most well-fitted and most appropriate model so far. In terms of bias and variance trade-off adjustments, when there were overfitting in earlier boosting models, I addressed it by reducing maximum tree depth, introducing subsampling, lowering learning rate, using Hooper laws, as well as increasing the number of estimators gradually. These changes reduce the variance without excessively increasing bias. The final model did not show a large train and validation gap, had stable cross-validation scores across folds, and demonstrated convergence in the learning curve. It also improved the MAE as well as improved the Kaggle MAE. One important insight from the process was that aggressively increasing model complexity did not always improve validation performance, or sometimes the improvement was quite minimal. Early gradient boosting configurations overfitted despite very low training error, and careful tuning of learning rate and subsample was more effective than simply increasing tree depth. Another key takeaway was importance of cross-validation. Single train test splits should have misled model selection decisions. Final learning curves were essential in diagnosing fit rather than relying on leaderboard performance. Leaderboard MAE alone does not review whether a model generalizes properly. In summary, to improve on performance, I transitioned from a linear regression to ensemble methods, tuned gradient boosting extensively, used cross-validation or robust evaluation, applied Huber laws for robustness, implemented ensembling. I also tried out auto gluon or auto ML, which basically automatically run a bunch of um, machine learning models on top of the data. And I also did extensive hyperparameter searching. Both did not improve the performance compared to the gradient boosting hand-tuned model significantly, and was in fact a little bit much worse, indicating that sometimes tuning the model is even more important than the model complexity. To assess and improve on fit, I deployed different learning curves for different models, monitored the bias variance behaviorally and systematically, adjusted hypermatters systematically, and selected a model with stable generalization performance. My final model achieves both a low MAE from the test and also from the Kaggle competition, um, maintaining a strong bias variance balancing and indicating this is a well-fitted rather than underfitted or overfitted model. That is all. Thank you very much.